Okay, very welcome. I think almost everybody here, lots of preparation in order to be able to finish this recording during the class. And before everything, welcome to week 3. Hopefully everybody got a chance to look at my announcement this morning about recording for the Miss lecture on last Thursday. Remember last Thursday, we had some weather condition. In-person classes canceled, but still I decided to record the lecture for you during the weekend. You may go to my YouTube channel. I already posted that link on the avenue for your reference. Go there, check the recording. You may say my face is really tired because I did it after 9 p.m. last night. So that's the reason, but still I tried my best to somehow review the entire requirement for programming using C in embedded system. I believe everybody at this point is really comfortable with the concept of C and why I guess.
Hi, so today are we going to go over that?
No.
I feel like we should have posted it a little bit earlier than this.
It doesn't have anything with that one. Today I'm going to teach you analog to digital. I'll explain.
So it's going to be something else.
Yeah, anything that I've already posted for you, if you miss watching it, it won't impact what I'm going to teach you right now. So
is that also true for the quiz then?
Everything I taught you during that recording lecture, again, everything in there, it was a part of lab 1 and 2 and whatever I discussed earlier. What I did as a review last night for you is nothing new. It won't impact even your quiz. I reviewed the concept that was the thing that I was explaining. I reviewed the concept of week 1 and week 2 in about maybe an hour and 30 minutes, a little bit less or more. You can go watch it later. I just explained a little bit more programs, C programs for you. If you go there, you can see. Do not create maybe some trouble out of that as an excuse. That anyway, everything in there is already shared with you during the lab time, during the last lecture on Monday, and even last week. So if you haven't had a chance so far to look at that recording, it won't impact your understanding of what I'm going to share right now. I'm not going to repeat that lecture, but still, you won't be impacted. Just watch it on your own time. And like always, you are more than welcome to either drop your question under that video for me. I'll try my best to get back to you as soon as possible. That's one method. Another method, as I keep reminding everyone, is come here. We do have discussion posts on their weekly modules. That's another method. I'm going to quickly even say which one. Look at here. This is the lecture for embedded system. The concept, or I would say the application of C for embedded system. And these are exactly what I taught you during the lab time, okay? So I just tried my best, exactly those programs that I taught you last week during the lab. In here, I opened them up, just explain them more. Same program, same concept, same for loop that I told you, hey, in here, you are going to use, for example, a for loop in order to create delay. Hopefully, everybody can remember. And quickly, to create a delay, you need such a for loop, right? Of course, that's not the best way of creating it. In the upcoming slide in here, I taught you even you can use MS delay as a command in order to delay the procedure. And look at here, all is somehow a review with lots of theory explanation about the difference between what is C, what is C++, and why I'm not using C++, because I had some kids asking me question, since we are more familiar with C++, why we are not using C++ for embedded system to make our life easier? You already know that. Why should we go through learning a brand new language? So go back to that recording. I answered all of those questions as a recording to make sure it is available to everyone. In addition, all of these examples that I have in here, In addition, remember, what do you have in here? In here, you have conditional statements such as like if, else, and all of those stuff, which or for. And in here, you can see also a little bit more about how you use if, else. And of course, in another one, in here, and you have switch case. So none of them new. Switch case I taught you last week. So nobody, even if you miss that one, you haven't still watched it, of course, go watch it. Definitely there is benefit, but still nothing is really new. Everything is a review. That one is a review of what we've discussed during the week 1 and week 2. Well, why I did it? Of course, for me, it was an additional thing to do. It was not something which is a part of my duty. I did it out of heart in order to make sure everybody is on the same page. And of course, to stick to the initial plan and not to stay behind. Otherwise, I have to call you to another extra makeup in-person class, which might not be easy for you to just maybe reschedule and show up. That's why I did it last night for you. Still, if needed, I don't mind to do another in-person one for that one. So today we are going to look at analog to digital. Analog to digital, the main explanation of it, I gave it to you during the last lab. And today I'm going to open it up with more detail and add a little bit of new information to the same concept. Before that, before I start this analog to digital, please let me know of any of your questions about the concept that we discussed last 2 weeks. I'm going to make sure everybody is clear. Then we can start this one. Anything for me? Everyone okay? So, in terms of big picture for the course, right now we are in here. Analog input. Analog input means I'm having some sensors such as temperature sensor, such as potentiometer, light sensor, joystick, any of those analog sensors that we've used during the last lab in order to just display the functionality of them on the LED. Those are all what we call them analog inputs. So, since I already gave you that understanding, and today I'm going to talk about the control register, it's much, much easier for you to connect the dots and understand what I am talking about instead of just imagining them, right? So that's the concept, or I would say this summary of what I'm going to share right now. After this one, definitely you have a better understanding of this type of conversion. I go back to the sample and hold module. Remember that schematic or diagram at the beginning of your lab, which I assigned it to your pre-lab. I'm gonna again repeat that one with more detail. And then I'm gonna look at the resolution, how we can change the resolution or how we can set up the resolution. We already did it during the lab. I said initially set the resolution for 8-bit. Remember, yes, your microcontroller is a 8-bit register, but resolution is different. I lose the words. Resolution, sorry. You can increase it. You can set it to 10. And after some of you already practiced how to change the resolution during the lab, I said, if you are, for example, for register 5 or register 2, either of those registers that I told you, put down the piece of code for them under the ATD. It was a void ATD function. All of those, remember, it was initially 3 lines for register 2, register 3, and register 4. Everyone can remember? And then for register 4, most of you for 8-bit resolution, your finding was 0x87 or 0x87 or 85. You can remember? That was your hex calculation or hex equivalent for resolution. I call it R8. But later, for those who were able to finish faster and go to the next step and set it to resolution 10. I said, kids, now you have to just consider 10 bit instead of 8 bit. And after you set back to a 10 bit, then instead of A7, you had it for 10 bits. For resolution 10, you had it 07. And then what was the output when you had more resolution? Who can answer this question? Go on, Nicholas. RGB LED. RGB in addition to for resolution 8 inside those setups that we had. Let me see if I have a picture in here, but I don't think I have a picture of the setup in here. With resolution 8, all you could see as an output on the LED being converted to binary. It was only reading, if it was temperature sensor, reading the room temperature in a format of binary only on port H, which was your LED. For light sensor, if you had your lights being covered, or if you had like more of lights being like adjusted in there, therefore the reading was converted only again for LED. For pot, also the same thing. You adjust the pot, you could read it as a number in format of binary, and of course you can again just convert binary to decimal and figure out what is the decimal number. But those who practice this part and under their void, they added 07 or 0x05, and so at the same time, not only they were seeing the binary equivalent in port H, which is those 8-bit, 8-segment LED, they were seeing it on the corner left as an RGB. RGB changing the color, RGB flashing, or so on. That's the summary of what we've discussed. Now, today we are going to look at the structure with more detail. So I'm going to start from here. What is analog to digital? Somebody answer this question. And why we convert analog signal to digital signal? Who can answer this one, since we already discussed it? Any idea, kids? Abdullah, I know you know it. Don't be shy, say it. Even wrong, doesn't matter. At least you are putting some effort. Say it. This is correct. Why you are not confident to say it? Anyone else who wants to explain analog to digital with their own understanding, you are more than welcome to do so. Okay, kids, analog is a type of signal which is continuous. And therefore, since it is continuous, it's not understandable for the machine, for the computer. Therefore, we need to discrete it. We need to convert it to, remember I said, computer, or let's say machine language, is a low-level language. Analog somehow is considered a high-level language, which is not really understandable for computer. We have to simplify it. Computer is not as smart as you guys are. Therefore, we have to convert it to binary. And this process of conversion, a continuous signal, like for example, this one. Suppose this is my X, which is time. This is time, for example. If I'm having a continuous signal like this, this is more close to human language. Suppose whatever this signal is, suppose maximum in here, if I call this one V peak, and of course, you know that what is peak to peak. If I call this one V peak, suppose this my V peak is just maybe 5 volts or whatever. But this one is not understandable for computer. I have to convert this one to a bunch of 0 and 1 in order to make it easy for computer to understand. And that process of conversion, which is not my manual work, is going to be the ATD, analog to digital conversion. So what does that mean? If I'm having the same one right in here, let me draw it. Let me give you some graphic in here. Simply means I'm going to have like very similar time in here. And I'm going to just split this one to different portions like this. I'm not going to get rid of any portion of it. Still, I include all of them like this. I still include all of them. All I'm doing in here, I'm gonna just make it little by little. For example, this portion is gonna be this one, and this one. And I continue exactly the same. But each time I only receive one of these sections. I send it in multiple efforts. I don't send the whole 5 at once to the microcontroller. Make sense? So far, makes sense? So the process is, instead of sending this whole thing in, let's say this is picture 1 or figure 1, figure 2, this whole thing is too much for the computer to understand and act on it. So I send it little by little. Next one, I'm sending this. Next one, I'm sending this. And this process is happening through compiler. Compiler, sometime for some microcontroller, is an extra module that you have to purchase them separately. But for what we have in the lab, it's a part of it's a built-in compiler. Therefore, it is done through that. So now if you consider it this way, this is a signal still. But this signal, for example, in here is maybe 0. Next time it becomes like this, a bunch of 0 and 1, 0, 1, 0, 1, 0, 1, and so on. That's what we call it, analog to digital conversion. Make sense so far? So now, this process is called encoding a signal. In order to split, this is an example, not always 5 volt. In order to split this to multiple pieces, that's what we call it encoding. We have to give it some procedure. That procedure has a standard method of calculation. I showed it in the lab, I repeat it in here. It's called successive approximation. So that's why I say you guys are not going to do it manually. All I want you to learn is be aware of which kind of method is used inside the microcontroller. That's all you have to do. So for example, I'm not going to give you a problem for midterm or final exam and tell you, hey, this is the problem, use the method, successive approximation method, and manually calculate it for me, right? So what I'm going to ask you, this method is going to happen through a step. That's why in here I have mentioned all of the steps for you. So initially, these are the 3 steps. Initially, it will go through comparison. Let me maximize. Whatever input voltage, in this example, and this is here, I mentioned 5 volt. Suppose my input voltage is 5 volts. This 5 volts in here is going to be right in here. It's going to my system right in here as 5 volts. Right after that, there is a block called control logic. In lab, in the register section, it was CTL. Can you remember? Can you remember putting lots of effort, learning how that CTL, or let's say control register, is working and how to adjust it for different purposes? That's exactly the same register, CTL. Now, CTL adjustment, yes, it is your job as an engineer to adjust it based on the application. But in reality, also you are going to adjust the information of the CTL register inside the microcontroller, but you are not generating information in there. You just go get access to that register inside the header file. For example, if it is, let's say, ATD 0CTL, can you remember that was the address inside the lab? And that was inside the .h file. And before this .h, we had the huge, or let's say a combination of letters and numbers, which is the name of the microcontroller. So, and then ATD 0CTL was the control for the analog to digital. And I ask you, hey, just power it on. That's the same thing. So this guy is in there. Information is given by the manufacturer. All you need is go find the right registered address, registered label, registered information, whatever you wanted to call it, and then bring it and set it to certain hex value. Next step, so first step is, again, information is going through the to the comparator inside the computer, and then this guy is inside the compiler, is going to review, for example, another thing to clarify in here. Remember I said if you get this one from the user manual, it doesn't have 0. And when you had it without 0 inside the programmer, it was black because something was missing. Therefore, that part is your job to make sure how to figure out the right information. And then I got you with me to come to the header file, and we notice all we need is adding a 0 right in between the ATDL and CTL. So that part is the one that you need. You get that, and now you are supposed to, for example, set it to 0xFF for output, 00 for input, if you want the entire register to turn on or turn off, or customize it based on bitwising. That's what the control logic is doing. Control logic is turning the analog, the entire analog, only with one first, actually bit 7. If you turn on the bit 7, remember it was a 8-bit like this. I'm trying to quickly review. 1, 2, 3, 4, 5, 6, 7. So that one is 7, that one is 0. Remember I said in there, if you turn this bit to 1 and keep the rest as it is, it's gonna power up the system or the register. That's what we did in there. Now, that's so. One more time, first step is you have to look at the comparator, means this guy will be converted to 0 and 1. It will be each time compared with the actual number, which is 5. And if it is right now, the number of zeros and ones that we have is equal to 5, then the process is gonna stop. If not, this is going through a loop. And it's gonna stay like a closed loop until the whole 5 is converted to 0 and 1. And we have the equivalent of 5 in binary. That's why when you look at the LED, suppose this is your LED. I draw this for a different purpose, but still right now, suppose now this is LED. If this is LED, that 5 is supposed to display in here. What is 5 in binary? 1010, right? Going back to this table, if I have it in here, I'm not sure. Yeah, I do. 1010. Therefore, that 5 is supposed to go through a process, be divided multiple times in order to generate something like 0 and 1. And at the end of the process, that one will be displayed right in here. So a step 1, compare. A step 2, go through the control logic. Control logic should be on. And a step 3, which is the main step, is in order to do that process of division, because it must sometimes, if the number is a big one, go through tens of division. Lots of division supposed to happen. Then that divisions is going to happen through successive approximation method. Therefore, you can simply say this is a method of conversion. And it is by default being uploaded and included in the microcontroller. So far, so good, kids. Make sense? Yes or not? Now, having that in mind, let me just add a little bit more in here for you, which is going to be backward. Why I say backward? What is DAC in here? So this method is working like this. Suppose you have a 2-bit successive approximation. This part of it you need to do manually, so learn it. So you have to have digital in here. When I say DAC, this one is again digital to analog, digital analog converter. You can say ATD, analog to digital, but this one is backward. In here is analog to digital. We have 5 analog. In here, this system is doing it backward. DTA, DAC, now it's like digital. because now after this method is already converted to some 0 and 1. It's not like number anymore. It's not decimal number anymore. Therefore, in here, this module will again convert it to analog. And that analog, suppose at this step, this is 4.5. And I'm looking for 5. Then this one again will come to this comparator, and comparator see, okay, 5 is not equal to 4.5, therefore I need another step. Maybe first time it is 2. 2 is coming, therefore 5 is not equal to 2, it will go through another step. Then it becomes 3. Then again 5 not equal to 3, therefore I need another loop. And so on until the entire 5, or until the conversion in here is equal to the actual analog number in there. Make sense what the process is? Clear? So that's why in here is backward. As I said, in here is opposite. Initially, I have 5. Then 5 is going through comparator, control successive. At the end of successive, it's not 5 anymore. It's a binary. And that binary first will be again inside, converted to analog to see, am I close enough to that 5? Or am I equal to that 5 or not? If so, it will stop it right in there and it will generate output for you. If not, it will continuously go through this loop until the output of here is equal to the input of here. Yes or no? Still with me? Okay. So now, question? Okay. Now let's review whatever I said. So I said, hey, digital to analog converter, I'm gonna initially, if I'm gonna do it manually, and I'm gonna teach you how to do it manually, set to half. So first, if it is 5 volt, it will divide it by 2. It will make it like 2.5. That's the first set. Let's say first, at the end, the first loop, this 5, first at step 1, the 5 is gonna be divided by 2. Then I'm having right in here, my first finding, let me write with different, my first finding in here becomes 2.5. And then this 2.5 is going to be compared. So as a result, 2.5 is not equal to 5 yet. Therefore, another step will be generated. Next time, input signal is still initial 5, but now it's 2.5. Now in here, I'm having 2.5. 2.5 is going to the system. Initially, this is V in. Now V in, because in here it became again analog. This is, I would say, V in 2. This is V in 1. Now V in 2 is this guy, is 2.5. Makes sense what I'm talking about, kids? Yes or no? So therefore, this time, 2.5 is going to the comparator, will be compared with 5. Still, it's not equal to 5. Then it will go to the control logic. Control logic decide to stay active and send it to the method or mathematical calculation, which is successive approximation method, to, again, for me, divided. This time, scale is 3 divided by 4. Means this guy right now, 2.5, is going to be divided by 3 over 4. Suppose it's a big number, and if it is a big number, initially 2, right? Initially 1 over 2. And then probably I'm going to write it like this. 1 over 2. Then it becomes 3 over 4. This is a step 1. A step 2. Somebody tell me what would be a step 3 if I'm having a big number. There is a pattern in there. What would be next step? 6 over 8. Next step is going to be 8. Well, how about next? 16. How about next? If it's a huge number, and this process continuously happen until I'm having the output of here be equal to here. Makes sense now? That's what we call it successive method of approximation. Any questions so far? I'm going to summarize in here. So suppose I'm having input voltage and I'm having another, this is DAC. DAC stands for digital to analog. And I'm having another one, I'm going to call it VDAC, digital to analog. And then this process is going to happen until, yes. I didn't get it. 6/8? Yeah. In here, I don't have 6/8. It's not that big.
Oh, it's the same as 3/3. 6/8.
This is 5. This is 5.
Oh.
That's typo. This is 5.
So the next one will be 7/6.
In fact, the reason for me to leave this one empty, because it's a function of how big the number is. That's why I cannot leave like a constant number in here. But this part is always constant. 4, 2, 4, 8, 16, and so on. Here is a function of what I have as an input. I leave it empty. So now, always, I'm going to continue until I have my digital to analog. My digital to analog, C stands for conversion, is bigger than V in. So I'll continue until I have this one. Up to the point that my input, if it is otherwise, my input is still not equal or less, I have to go and repeat the same process over and over and over. Now, in this process, I'm going to add a little bit of detail. Remember the sample and hold. Sample and hold block. That sample and hold is right in here, kids. This is where that block is coming. So the voltage is sampled, and whatever I have from that voltage inside that like capacitor, remember the style was like this. I did have one switch, and then right in here, I had a capacitor. Can you remember? And this capacitor, it was grounded. And this block, still I had another one in here, was called sample and hold. So this block is right in here, right after the input voltage. Each time, even after I'm receiving something from the AC or DAC, it will go first to the sample and hold. A portion of it will be holding here as soon as this switch is closed. And then this one becomes the next input, which I said it, I believe, right in here. I just wrote something on top of it. Next time, that will become my, let's say, input 2, input 3, input 4, and so on. Make sense for everyone?
Is every input half of the previous one?
I'm going to come up with some example. Pardon?
Is every input half?
No, that's why I say 2, 4, 8, 16. But top is not, for example, something that make it half. Not necessarily. In here is like 1, in here is 3, in here might be different. So, for example, if I have 5, not necessarily next time is 2.5, not necessarily next time 2.5 to like divided by 2. Not necessarily. So suppose I'm going to have, let me do one example. V in is what I can use, maybe 11.2. I'm going to give it decimal point, much easier to understand. What step do I'm going to call this one my input voltage. I'm going to go through a sample and hold. This is my input. I'm going to go through a sample and hold, and I'm going to have a comparator. This is my comparator. One of it is coming here. Remember, this comparator is supposed to be connected to what module? Who can tell? The input for comparator next time is not the real input. DAC. Then this guy is connected to DAC because it should compare this input with the one, let's say input D. I call it input D. Each time may change. Input 1, input 2, input 3. These two supposed to be compared, this and this, inside this comparator. So far makes sense? Let me see if I can slide over or make it smaller to draw the rest of the circuit. So now my input right after that is going to another module called control. Right in here, output from here is coming to another one, which is CTL. CTL, remember, stands for control logic, control module. Right after that, this is the time which is really fun to learn. I'm drawing it this way to have enough space. In here, you see I'm having SA. I'm going to call it SAR, successive approximation register or method, whatever. I'm going to call this one SAR. Now, this SAR supposed to generate binary. Binary means for the first step. If I had, in this example, 11.2, initially it has to be divided by this, right? So then I'm going to have a bunch of numbers. Somebody do it for me. Then what is the binary equivalent? Binary equivalent will be 1, 1, 0 will be 1. Suppose I'm going to have in here, this one, I'm going to have 1. This one, I'm going to have, if it is 11, okay, it's going to be 0. This one, I'm going to have 0. This one, I'm going to have 0. I'm including all the outputs in here for you. So it becomes 1, 0, 0, 0. But 1, 0, 0, 0 is not equal to what I am looking for. Right after that, this number, somebody can convert 1, 0, 0 for me. It's easy. You don't need conversion. You need to only check either the table. 1, 0, 0 means what? Inside the DAC. 1, 0, 0, kids. 1, 0, 0 is this one. Means, where is it? Means 8. Means 8, right? Right now, in the first round, in here, 1, 0, 0, 0 means 8 in hex. Yes. By dividing 11.2. 11.2 is my input. Remember I said your first scale is 1/2. Make it half. Make it half. 5, but when you make it half, but this one is 1, 0, 0. It doesn't have option to show decimal. It won't generate anything close. 11.2. No, this one is a 4-bit register. It's not 8. If it is 8, yes. For example, after this one is divided, it will create something bigger. Something, actually 6 something. But this is a 4-bit. It's not an 8-bit. Since it is a 4-bit, you can have it 8-bit as well. Since it is a 4-bit, it will generate 8. That's a little confusing, but I'm explaining. Right after that, now what do I have in here? This guy, after DAC, supposed to, remember this is the same in here, so I'm going to remove it from there. This is the same as the one in here. I'm going to connect these two together. This guy is supposed to come here. Right? So then, suppose this is my VDAC. VDAC. And I have another one in here. I'm going to call this one VREF. VREF is what I have in here. Now this one will be doubled. This one will be doubled as a reference. And these are not what you can do. These are what inside here. After it is generated, it will double it. And then my reference will become 16. Reference right now is 16 volts. And then now this reference will be transferred. So initially I had 1, 0, 0, 0. And then my reference right now, as I said before, this my I put it in here. Reference is changing like this. 16, what I have in here is gonna be my B0, B1. Let's say these are my bits. Maybe I'm gonna call this one like different B's in here. Then I'm gonna have B0. Let me bring it up and then just underneath. So I'm gonna repeat it in here. VREF, my initial one, B0, first one, 16. Next time, it will divide it. Divided by 2, then B1, 8, the one that I have. Next one, it will again divide it by 2. Next one, again divided by 2, and then now I'm ready. This one becomes B2, this one becomes B3. That's why in here I told you, remember I mentioned it right in here, I leave this empty because this each time might be, in here it is 3 because I had 2 bits. Since I had 2 bits, first it was 1/2, next it became 3/4 because it was 2 bits. But in here I'm having 4 bits. That's why I say I leave this empty. It's a factor of how many bits I have. If I have 8 bits, it's gonna be different than when I have 2 bits or when I have 3 bits or so on. Now, let me draw this one to make it a bit more clear for you. I'm gonna convert it inside here now. What's the equivalent? V is right now reference. Yes, I hear. Yes. LCD? We didn't use LCD. You mean during the lab? More?
Yeah. Right there. You have 1, 0, 0, 0, and then another where I get it. Is that what you put in?
Initially, yes, because initially you have only one of them active. That's why we say 1, 0, 0, 0. Next time you toggle next one. Next time toggle next one. Next time toggle next one. Make sense now?
Yeah.
It's 4 or 2 or 8. These are what the problem will give it to us. Problem always has like in here. Look at here. In here I said I'm having a 2 bits. Next time if it is a question in exam, it might be 4. It might be 6. You don't have to guess. You don't have to memorize. That's a part of the problem.
Then if it was the first 2 bytes.
Yeah. If it is 2, then it is like this. Let me clarify that for you. Then you do not have this 2. You have only this 2.
So
then you have only 2 steps to go through it.
So
1, 0, next time 0, 1.
And then
no, still more. 1, 0, 1, 0. If it is 2 bit, it's a function of what is the number as an input. So you may have 0, 0, 1, 0, 0, 1, and 0 and 1, 1.
Right.
And if it is, this is for 2 bits. If it is 4 bits, again, all of them 0, all of them 1, and each time 1, 0, 0, and continue until you meet all of each of this being toggled one time. So more combination.
Yeah.
Make sense?
Yeah.
You got the point?
Yeah.
And for example, if it is 6 bits, different, but a still method is the same. Just number of bits are gonna be different. So now let me draw this one. So I said I'm gonna have initially for the first step, how many steps I had? 1, 2, 3, 4. So I'm gonna define it to 1, 2, 3. Because if you learn this example, it's gonna be easier for you to follow the next one. So I already said, okay, it's gonna, since this is a 4-bit, right now I'm practicing 4-bit for this one. Look at here, 1, 2, 3, 4. That's why we say 4-bit. And again, always I tell you, what is your successive approximation bit number? So if I have 4 bits, for the first one, what was my reference? My reference was my VREF was 16. right? And for the second one, and for the third one, still I'm 4 bits, means right in here, between those two. Still I'm looking at 4 bits, still I have 4 bits. But what is the input? Input supposed to finally shown in here, input, it was 11 point, what did I say? 2. This is going to be my input. Now I'm going to just do it in here. Initially, if it is reference is 16, reference 16 I converted. It was 1000. That's my reference 16. Means 8. This is my first part. This is binary and this is hex equivalent. How about this part? Part 2, I'm gonna now, so this one is 8. Now, next time, my reference is changed. Therefore, now next time I'm gonna toggle. So it was 100. If I toggle and turn on next one, means if this is this one, 1, 2, 3, 4, 5, 6, 7. Initially, I turned on only this one, generated 100. Now I'm gonna toggle this one on too. Then I have 1, 1, and I have only 4 bits. So 0, 0. Now makes sense what I do? Each time I toggle on one of them, you are gradually getting it. Stay with me then. Then what is the equivalent for this? Who can say? 12. 12. But we do not have 12, right? Yeah, but still, since we are converting to decimal, this is 12. So far, we toggle this one on and this one on. What would be next one? Now I'm going to toggle this off again. So still I keep this one. I toggle this one. And this one is again, now I'm going to turn this one on. Then I have still 1, 0, 1, again 0. 1, 0, 1, 0. 1, 0, 1, 0 is what? 10. Stay with me. Next one. We are getting closer. Now my reference is 10. It's going up to this system. It's going up to from here to here. And now I'm still writing here 10. Close to 11.2, but it's still not accurate. Yes. Why I go from 12 to... Because each time the reference will change. Each time I turn on one of this, and one number will be generated. Either it is less, either that number, this is my input, 11.2. Each time that I convert, either the VDAC is greater than this guy or less than this guy. And I'll continue until I am equal. I don't want either of them. I don't want to be greater. I don't want to be less than. I want it to be equal. Therefore, I continue until I can generate something equal. The reason is when you convert this one, each time, remember again, I said this is a 4-bit. So when you toggle one off, another on, one on one, and then another off, numbers will be generated and converted. So for example, initially 0, 0, 0, and then if I toggle one of them on, I started from 1, 0, 0, first one. Then it became 8. Next time I kept that one, I toggled next one, then it became 12. I added another one, I turned another one on. Click, good?
So why
There is a standard in there. I cannot adjust everything. I wish I had that much freedom. Everyone is getting it, right? Still, let's continue, finish this one. Hopefully by end of this drawing. Kids, I know this is new. Stay with me. We'll practice together until everyone is comfortable. So now my reference is 10. Still, I go through comparison. VN, VDAC. Now, 10 is less than VN or greater than in. 10 is less. So still another one is going to happen. Next time, I am in this step, 1, 0, 1, 0. So I keep the 1, 0. And this time, I'm going to turn this one also to 1. Then it becomes 1, 0, 1, 1. Now convert it for me. What's the equivalent? 11. Good. Okay, now 11 again is a comparison in here. This guy is doing the job for me. It's comparing, as I said in here. Now 11 is compared with V in, which is 11.2. Still, V in is greater. Therefore, I have to go through another process, right? So now this time, I have 1011, which is 11. I repeat it because there is nothing after that to turn it on. So since now it is a repeat, compiler will stay right in there because compiler doesn't have decimal points in there. Therefore, it will stay right in 11. It's very close. If it was 12, that was a different story. If it, yes, then it becomes more. I don't have to become more. I have to continue. I have to continue to make sure it is very close. 11.8 is not close to 11.2. Of course, 11 is closer. It won't because there is no option for me to generate 11.8. Oh, you mean the input being 11.8? Oh, okay. If the input is 11.8, then it's not going to be 4-bit. Then I'm going to have an 8-bit. It will round it down. If it is 11.2, I don't use 4-bit. I said it. I have 4-bit in here. Get the point in here. I have 4-bit. And that 4-bit is a function of what input in here I have in here. If I'm dealing with a bigger number, then definitely I have to choose a bigger bit for my method of approximation. Then I do not have 4-bit. 4-bit won't generate a number which is, if this one is, as you said, 11.8, this guy, it won't, 4-bit won't be able to come close to 11.8. Maximum for 4-bit in here is going to be maybe something at around 11. Therefore, I cannot use 4-bit anymore. I have to use 8-bit. Means I have to have a bigger one in here to be able to generate more than 11. Still 4 works. Still 10.8 is close to 11. Reference is 11. Look at here, reference is 11. Either point to up or point to down, it will close it at 11. And anything more than that, I need a bigger bit.
So if it was 11.8, you give us
6-bit, 8-bit. Yeah, I'm mindful. I know that's impossible. Nicholas, clicked or not? Yeah, okay. So kids, I think it's a good time to give you a few minutes of break. Maybe a little bit talk to the person next to you. Discuss what I explained in your own language and bring it to my attention. I'm still here. I'm going to give break, but I'll take care of your question. Then we'll continue.
You go direct. I think it's
No, 4 bits is 4 bits. It's a number of not bits, function of number of bits. Yeah, that if I have 4 bits, for 4-bit becomes 16. If I have 2 bits, this is going to be my DRAM.
before.
No, before.
Before. So
If I have, for example, more, then it becomes 32. It becomes this. So 16 is not my guess. It's not my choice. It's a function of how many bits I have in here.
standard.
This is standard, yes. This part, that's why even in here I said this is a standard, but top, the B are gonna change. But in another node somewhere, I have too much in here.
So if it was 2 bits, it'd be 4.
Oh, here.
Yeah.
In here, for 2, and then for 4, and then if you have 6, it's gonna be different. If we have 8, it's gonna be different. This is standard. So 2, 4, 8, each time double it. 32, and then 32 by 2, and then
But it doesn't seem like if you scroll down, it doesn't seem like the 16 affects the calculation. So type of 8 out of 8.
just a reference to compare. In here, it will compare with that in here. Because this number is the reference. Look at here, it's loose.
So what does the reference do? What's it for?
Just to confirm, I'm calculating for it. 16 is not going inside the comparator. The number of the DAC is going. That's why I left it loose. That's my reference point. To understand, I'm using 4. You can even avoid having this in here.
So what goes back into the comparator is your
Is the calculation,
calculate.
like in here is 8.
8.
With that. And the next time is 12. And the next time is 10. And next time is 11. And when 11 is here, then 11 will be compared with 11.2. And then it's time to stop.
Less. And if you do more, it's going to go higher.
Input should be more than the DAC.
Yeah. Okay. Okay. All right. Thank you.
No.
is the reference voltage?
That's what it is. Reference voltage is a function of how many bits I'm gonna use for conversion. If I'm gonna use four bits, 1, 2, 3, 4 bits is 16. If I'm gonna use 2 by 2 is 4.
So these four volts.
If I have 2 bits in here, then reference start from 4.
So on a question on the test, would you either just give us the like a reference voltage or the number of bits? And then we'll figure like no.
Right.
Okay.
You want to see a lot in there.
So if it was 8 bits, it'd be 32.
8 bits?
It would be a 32 reference voltage. Right. Okay. And then what is your your sampling? This is nice sampling. Your plus minus box triangle where you have the 1/2 step. Yeah, but you said,
What is what?
yeah, your comparator.
Comparator is taking whatever from DAC
Yeah.
and it will compare it with my input to make sure, do I need another step or not? That's what my comparator is doing. It will compare my initial, this one always will stay as it is. So on my comparator, I have 2 legs. One of them is constantly my input, and I'm gonna explain it right now why I have to keep it constant. The reason behind why I have to keep this one constant is exactly this picture. Simply because my time of conversion for each step must be the same time. If it takes, like, for example, 5 seconds, it has to be 5 seconds for all of them. That's why I must keep the inputs to go to positive for every single step, regardless how many steps I have. That's the reason behind it. And then each time, of course, again, this is V in, and then V DAC needs to be, this is comparator, comparing with what? With V in. Makes sense now?
5.6.
How to?
How to convert 5.6 in 4 bit to 1000? It's using this thing, right?
5.6 is more closer to using a 2-bit.
Yeah.
You can use a 2-bit, you can use even a 4-bit. So the first one, if it is a 2-bit, you have 0, 0.
0, 0.
0, 0. So it's always, this is always the same thing. You have only 4 condition, right? For 2-bit. You're having a 2-bit like this.
It can be 0, 0, 0, 1, 1,
Yeah.
0, 1.
I said it before in here. These are what you have.
Yes.
And each time you have to toggle to meet all of these 4 conditions.
That part I understood. But the first step we did, which was 11.2 divided by 2, made it 5.6. And we have to convert 5.6 to integer, right? To get the display. So 5.6.
No, you don't divide it in here. If it is a 4, how you define it is just initially it's 0, just start toggling this to 1.
Yeah, that's okay. I understood the toggle part. But no.
That's exactly how I created for 8.
Yeah. But no, the input voltage is 11.2. And comparator divides it first. Correct? By 2, what you said. And it's 5.6.
No, comparator don't divide it.
What is the first thing?
Approximation.
18.
No, it won't divide the 11.2.
What is?
It won't divide the actual number of the inputs.
So we just starting with the first toggle, 1, 0, 0, 0.
Let's just start with the first toggle.
And then we approximate up or down until we reach there.
It's approximate.
So
The name is talking for it.
But with 8-bit, we can go to decimal.
With 8 bits, what?
Can we go to decimal to 11.2?
No,
So how
we never have decimal in there. We always have close.
so you keep running?
You keep running to come close, very close.
No, like this is 4.
Because in binary, we do not have decimal. Do we have decimal in binary? No, always approx. That's why the name is
So this will never
approx.
stop. This will keep running because it's under 11.2.
No, it will stop. As soon as it comes close, it will stop.
Okay, so it will do one extra step and then stop.
Yeah, because in next step, it will be repeat.
Same.
That's why I say I want you to just add at some point some stop for it. And that's why we say, hey, put it inside the for loop, give it a clock time, put it inside the for loop and say, start from here, stop in here. We have to manually stop it. As soon as it is coming close, stop it. So let's resume. Kids, let's resume. So let's resume. Otherwise, I won't be able to finish it one more time before I add more. Reference point or voltage, reference voltage is a function of how many bits I'm having for my approximation. Or right in here, I said the name is talking for successive approximation. Approximation simply means it's not always exact number if I have decimal point. It's an approximate number, very close to the number with the digit or let's say integer, right? Not to the decimal. Therefore, that's why we call it approximate. Why is that? Because we do not have decimal point in binary, do we? Do we have any decimal point in binary? No, we don't. Therefore, we can never create exact. We come close, approximate. Again, I'm going to show the table. Do we have any decimal point in here? We don't have decimal point in here. We only have in decimal, if I'm going to, or in hex, if I'm looking at hex or if I'm looking at decimal, none of them comes with decimal point. Let's say decimal. Decimal, I have up to here 7, and then in here I have 8 and 9, and then even 10, 11, 12, 13, 14, 15. I do not have 11.2 in here, right? Therefore, as soon as the approximation method meets some approximate value in here, which is close to 11, it will stop right in there. Because in here, I do not have any binary equivalent for 11.2, 11.6, or I think it was Nicholas, 11.8. I do not have decimal point. Make sense? Therefore, it will come up to approximate number, which is close to that input number. And one more time in here, what it is happening is I draw it manually, so it might be much easier for you to understand if I show you this one again. Because I'm having 2 inputs in here. Let me clean up and say it again. I'm having 2 input to my comparator. Comparator, the name is, I believe, clear. The name is comparator. Means at least I have to have 2 values to compare them, right? Therefore, one of those 2 values is always my input voltage. And that's, for example, in this case is 11.2. I keep that one constant, and I'm gonna now add more. Why? I keep this one still be one of, in this example, 11.2. In other example, might be anything else. This should be always coming to this point. I never change this point. All I change is this point coming from DAC, digital to analog converter. This one is variable. This one is constant. This one is variable. It keeps changing after each sequence. Now, this and this must be compared in order to see if I need another step or no. Now, why should I keep this one constant? That's a good thing to learn about it. Simply because, remember, we do have clock inside the system, right? And we can calculate that. And of course, if you look at this one in here, I have a sample and hold, which I said. This sample and hold is exactly what I can just put it right in here. This is my sample and hold box module. This guy will sample exactly with the exact amount of time for each step. For example, if initially it takes 5 seconds to go through this process, in the second step, it shouldn't take maybe 7 seconds. It shouldn't take next 8 seconds. It should always be the exact same time, because we are going to generate zeros and ones in order. So that's why sample and hold in here is doing that job for me. Means that switch, which is, I believe I draw it in here, the switch will close and open in the exact same time for every single sequence. Suppose if it is 5 seconds, next time again, it will Take only 5 seconds for the switch to close, send the next voltage to the capacitor, then capacitor hold it, then send it as my next VDAC to the comparator. Make sense, kids, what I said? That's why, because each of this, look at here, must be exactly the same. And that's the job of that sample and hold. If it is not equal, then I'm not going to have an accurate conversion. Time must be equal. So if this is 5, this should be 5. And even in here, it has to be 5. And this is times, and this is S. Suppose this is 5 seconds. Make sense? That's the reason for me to have always constant input in here. Constant input, constant time. And I have it right in here. Kids, remember I said I'm going to open up sample and hold one more time. So conversion time must be a constant. This is again summary, a constant time. I cannot have it variable. All I can have variable is VDAC, DAC in here. So that's why most of the converter, they do need a sample of voltage to go inside. This is my sample and hold. And inside here, I have a switch, I have a capacitor, and this is grounded. And then I have another block, right? So now in here, this is the same. This is my switch. Let me maximize one more time. So I'm having an amplifier right in here. So amplifier means what? If you know a little bit of electrical engineering, combination of a switch and a capacitor like this is what we call it amplifier. Make sense? So now in here, I'm having it right in here. This is my sample and hold. The whole block, but this is my amplifier. I think I already mentioned even what is amplifier. Let me see. Yeah, I did. So amplifier is a capacitor and a switch in series connection. This is a series connection because only one end of this is the switch, this is the capacitor. One end is connected. This is a amplifier. Make sense, kids? So far, so good. Now, once again, sample means what? Sample means this switch is closed. When the switch is closed, means a voltage will be sent to capacitor, and that will be my sample for the next sequence. Hold means what? Hold means when the switch is open again, and now capacitor is holding the previous voltage for me to become the input for the next step. I love the fact some of you are understanding it. Still feel free to hold, like pause me, ask question. Honestly, I love that. If you ask questions, simply means you have your attention in here. So now you know what I did? Sample and hold. Have a great understanding of this part. This is pre-made, ready, is inside the module. You are not gonna manually connect a switch, maybe a capacitor on breadboard to do the sample and hold. It's inside the chip, inside the microcontroller. So far, so good, kids. Now, if you have that good understanding of the conversion process, which I tried my best as much as I can, simplified it to make sure everybody at least have a like clear understanding, it's time to say, okay, next step are gonna be easy for you to understand. Before that, kids, this course is an advanced course. Most of it based on electrical engineering understanding rather than mechanical engineering. Therefore, I do not expect any of you to bring any previous knowledge to the class because you are not electrical engineering students, you are automotive engineering. I know that. Okay, I don't judge you, I know that. That's why I'm trying as much as I can to simplify and share basic stuff. Saying that, I mean one time listening in here is not really listening, it's hearing. You just hear them. Hearing and listening are different. I told you before. Hearing is just something is going on, some noise, but I do not have my attention on that. Listening means energy and attention, because our energy is where our attention is. When you listen, your body is here, but your attention might be out of the class. To make it short, watch the recording at least one more time if you want a good midterm exam. Every single recording, you guys you know that how much effort I'm putting into this. While my teaching schedule, Nicholas saw my teaching schedule. I don't have even 10 minutes between my classes to eat. But still, I do this for you because I know this course is a heavy course. Don't think this is a joke. Also, you have my full support day and night, but don't make it like something that I can learn overnight. You cannot. Years and years, I'm teaching such an advanced course. If you follow me weekly, stay with me weekly, learn weekly, then you can be successful. I told you during lab 2, I'm always flexible and supportive to you. I believe after years of being together, you know how much I love students and how much but lab 2, I was not flexible. Again, why? Because I love you. If I stay super flexible in lab 1, 2, 3, you won't learn. Copy and paste, and then you are stuck. That's why lab 2, especially Friday section, you can confirm. I was not flexible at all. If I come there, if I ask, if you have answer, I'll mark you. If not, out of heart again, not to be mean to students, I don't mark you because I know you will suffer later. Do I want you to suffer? No. So if sometime I'm not really easy on you, again, that's because I know what's next. If you miss it, you are gonna struggle. Stay with me, interact with me. I love that. Any question? Even midnight, if I don't have during the daytime, I'll try to respond. Okay, so now let me continue because we are getting closer to the end of the class, and I'm gonna also quiz you if we have time. And I have a lot of solved example. I try to see if I can solve some of them. I already solved few in here, but I'm gonna see if I have time. If not, next session, and of course solutions are already posted. So let's look at this one now. You have that understanding. This is the resolution. Remember I said it during the lab time and at the beginning of this lecture. Resolution means I'm going to have a more accurate voltage out of this VDAC or no. More accurate means what? Means compared to the input voltage. Again, remember I said it's approximation. I never could have 11.2 in this example. Therefore, if I would say increased resolution means I'm gonna have more bits. And that's again going back to the same challenge in here. If you want to increase your resolution, increase number of bits in here. Initially, I told you 2 bits. You want more accurate, then make it 4 bits. You want more accurate, then each time I'm adding more bits to that resolution means I'm having a more accurate number. Now makes sense what do I mean when I say increased resolution? Same for your electronic devices. That's why some of the high quality, let's say cell phones, because everybody has that one. If you have a high quality cell phone, when you are filming and then it does show, like for example, stronger resolution, better resolution means more accurate conversion in here. Same with your screen. Now you have a better understanding of, regardless of if it's my microcontroller in the lab for automotive application or any electronic component, these things are the same. So far, I believe none of you had the good understanding of what's resolution, technically. Am I correct? You just know some numbers. Now you know what is resolution and why a better device is more expensive. Because there should be more RAM in there, more capability of going through more process. Speed should be faster to finish up all those processes and finally generate a more accurate result. That's why high quality devices, not only they have high resolution, which is a good part of it, of course they are costly. Makes sense now, right? Good. So now let's look at this one as another example of resolution. Suppose I'm having ADC. Again, now everyone now knows ADC means analog to digital converter. I'm going to have some analog signal any input, and then I'm going to convert it. During this process of conversion, I have to look at some information such as 1 and 0 as binary format. And in here, now I don't repeat all of this step. This guy is going to do the job for us. Now resolution means number of conversion in here. But still remember, regardless of what is the number of conversion, still my input is going to be always in here constant. So for example, I'm converting maybe something at around 10. This is my maximum, which I'm going to convert. Look at here how many steps. This pinkish, I don't know what color, green, like maybe reddish, pinkish, whatever. This one is my analog voltage. This step one, this blue one is my digital voltage. Make sense? So I'm converting this constant analog to this combination of 0 and 1 in digital. Now somebody tell me what is the resolution in here. What's the resolution? How many bits do I have in here? 3. So my resolution is 3 bits. Right? My resolution is 3 bits in here, in here, in here. How about here? It's a longer one. What does it mean? Means I had more conversion for that step, because this is going to be your peak voltage. Therefore, in here I have 16 bits resolution. Now let's practice one together, how this is happening. So one example. Clean a screen in here. Example is asking me, I'm having a 2-bit ADC. Pay attention, next week I'm going to give you in class assignment to complete it manually, either on a piece of paper, it's going to be your option, either on a piece of paper if you have tablet or any option to write into your electronic devices. I myself, even I have pen on my cell phone. Even you have pen on your cell phone, okay. Any way that you can have manual calculation. If it is electronic devices, easy. You don't need to take picture or something. Just quickly upload it or save it as a PDF, upload it to Avenue. If you are writing like on the paper, just take a picture. No difficult time. Upload it on Avenue. That one will be in addition to your quiz. So I'm going to look at here, 2-bit analog to digital. What's my number which I'm going to convert? 0 to 5. When it's 0 to 5, kids, we are going to draw this one, means maximum is 5 volts. And I'm going to start from 0. And this is going to be my time. I'm converting 5 volts. But I have to start from just some division. So if it is binary 2-bit, means I have to go through all of this steps. 0, 0, 0, 1. Next time I toggle it becomes 1, 0. Next time both of them. So it's a 2-bit. Means I have like 2 bits like this. Each time I have to turn one of them on, another off. Sometimes both off, sometimes both on. Everyone has this understanding now, right? So let's do it. For 0, 0, which is going to be my first step, I'm going to start from 0. And then if I convert it for the first step, it's going to be something. This one is for the first step. 0 to 1. Maybe 0 to 1. It's going to be the first step. I'm going to say 0 to 1, maybe 1 to 2. And I'm going to put them down. 0, 0, 0, 1, 1, 0, and 1, 1. For each of this, I have to do the conversion. For the first one, if I do it, becomes a 0, 0. It becomes what? It becomes right in here. This is my point, which is something at around, I have 5 volts. First step, maybe 125. Again, I go through it. You divide again, and then you go through it. Suppose this one is happening in here. I'm going to draw it with a different color for you. It's going to be right in here. This is the first one. And I started from 0, therefore this is 0. Now I'm going to put 1 in it. 0, 1. Means I'm going to keep this one 0. but I'm gonna put 1 in it. 1 in it becomes right in here, for example. So, but still, if this is 5 seconds, again in here should be 5 seconds. None of this could change. All of them should be 5 seconds. Time is constant. I cannot change it until I'm closer to output or V peak. In there, some step might repeat, like the one that I did for 11.2. I went through another extra, therefore that's a longer one. Numbers are matching. In fact, it is 2 sequence. But since both sequence, their output is the same output, it seems like a longer time, but in reality, it's not a longer time. Make sense? So now, I'm going to do the next one. Next one is right now 2.5. 2.5. This is going to be something at around here. 2.5. Next one is going to be 3.7. Next one is going to be last one. If you convert it, very close to 5. Right in here. So now, if you connect them, of course, these are all, again, as I said, equal. And then in here, again, it has to be equal. This is next point. And then again in here. So then from here, I'll go to 3.7 up to here. But in here, 3.7 is going to be the last one. It may take longer because it may repeat. And it will stay on that constant number up to I generate maximum, which is right in here. This is going to be my B in, equal to B in, which is almost 5. So now I'm going to draw the equivalent in analog. Suppose this is your analog. Just connect these things. This. Suppose this is your analog. It's not easy to be really accurate, but I mean, these things should match. So this is your V analog. And what I have in here in red, this is your V digital. Make sense? I think I have time still to do another one for you to make sure it's clear before I leave. I don't quiz you probably. Now I quiz you next time. So somebody may ask me, how did you do that? Because I can tell that from your faces. How did I do this? Any idea? Any idea? It's a 2-bit, right? I mean, means what is my VREF? I said it in the previous step. 4. So then what was my V in? 5. Now what is my ref? 4. Then it becomes 5/4. Make sense? Then what is this? Do it. 1.25. That's how I found this number. Make sense? And we continue the same to come closer. You got it? Okay. So let's do another one. Do I have another example for you? So before, let's just give you the same thing. Resolution, I just said it in here. Resolution, right, means get your VREF. In this example is 4. That's how I calculated that one. Your reference voltage divided by, in this example, I know this is 2-bit. But there are situations you want a general equation. General equation means 2 to the power of n, and that n means number of bits. Now you know how to start with calculation. Make sense, kids? One more time. If I have if I have 2 bits, should be 5/2 to the power of 2, means 4. If I have my bits are 3, then it should be, this is 2 to the power of 2. Then if it is 3, it should be 2 to the power of 3. To the power of 3 is what? 8. Then I have to start from 8. If I have 4, somebody tell me, should be 2 to the power of 4. Now you get the point. This is how you know what number you should pick for your reference to divide by. Now let's do this again with this understanding. Now you know, if I'm having 5 and I'm having, this is your in, I'm gonna use bit 3. If I have 3 bits for resolution, then first I'm gonna calculate my resolution. I just said it, this is the equation. My resolution, I say just R. My resolution is 5 divided by not 3, 2 to the power of 3. Make sense? Which is 8. So now 5 divided by 8 is gonna give you the first point, which is 0.6 something. And now if you want to draw it, the first one, since it is a 3-bit resolution, means you have like 0, 0, 0. You start from 0, 0, 0. If you start from 0, 0 and this is your 0, 0 point, then whatever you find right in here is gonna be 0.6. Makes sense now? Yes. For the second one, yeah, like what I did in here. So for example, I did 2 bits in here. So let's look at this one. Let's calculation.
Above, and then we went with B in the second. There is why you switch those the numerator of that.
I didn't switch. Oh, these are 2 different examples. N may change. 2 to the power of 3. I don't get it.
So in the above example, we did our voltage reference over to the power bank.
Oh, this is resolution.
So then
You mean in here? You mean in here? In here when I was calculating? You mean this one? No. In here, this is resolution. Okay, I got it. You mean why the voltage reference is equal to V in or not? Why I put my voltage reference to be 5 in here? That's what you say?
yeah.
And then what is this then?
So I understand the bottom part. It's just you did 2 different ones in the 2 examples. Like first one you use voltage reference, but they don't equal each item.
Okay.
Is there a reason where you use each one?
No, I got the point now. So in here I said voltage reference. For example, if you have a 4-bit, your voltage reference is 16, right? But in here, I was not talking about the resolution. I was just talking about your reference. But now you say, if I want to just do reference, why in here, you say...
Yeah, so that way you use your VS equal to 5, but above you use the voltage reference.
In there, I just use VREF as my assumption. As my assumption, not as the equation to... You are right, that may cause confusion. In there, I use VREF as of my assumption of how many bits I have.
Yeah, I get that.
Okay, in here is a different story. Maybe I have to reword this one to call it something else. Maybe I have to say VDAC at each step or something like that. Maybe I shouldn't use reference there to cause you confusion. Voltage reference is always, we continue with that voltage reference up to come to Vin. Voltage reference means the one coming out of V digital to analog. When I in here look at the resolution, I'm gonna say my voltage reference at some point maximum is maximum of VDAC. That's why in here my V in and V reference, which is the VDAC, all of them are the same, and I just put 5. Because for resolution, all of them should be the same.
They all should be the same.
All of them should be the same to figure out what resolution I want. Now make sense? Okay, voltage reference is the maximum number I'm going to start with to do the divisions. And that maximum number should be a number which is going to become closer to input voltage. Now, at some point, my maximum number should be 5 volts out of the VDAC. Very close, either maybe bigger or equal, very close, or less than equal, very close to that. In that situation, anyway, VDAC is the same as VREF. Now makes sense? These two are the same. These two are the same. Are you sure?
Yes.
Okay, now for resolution, either you can in here say VREF, but not the instant VREF, the maximum VREF. And maximum VREF at some point should be equal to VIN. That's what I mean. Now let's just give you that equation. VREF should be V reference high, or that maximum I just said, reference high, because VREF has a high. Like for example, if I'm gonna say in here, I'm gonna start from 0 to come to 5, I have a VREF low and I have a VREF high. That definitely will solve your confusion. So I have the maximum and minimum of reference voltage. Minimum means I'm gonna start from 0 in here. This is my V reference low, and I'm gonna end up at V max if this is my max, and max is equal to V in, therefore my VRH is in here. So all of them, if I consider the max, then are the same. Now makes sense? So now to calculate VREF, I have to have this maximum. In this example, my maximum is 5, and then I have to have the minimum. Minimum is VREF low, and low in this example, for example, is 0. Therefore, that's why my VREF is equal to my VIN. Now makes sense? Ella, it makes sense? Okay, now let's derive it. Now you know what I did? I just put the number each time in this equation, and that's how I generated. So each time, for example, if it is a 2-bit, I said 5 divided by 2 to the power of 2, and I continue this until I come closer to this point. So I believe I won't get time. This is one of the most important example, right? Which definitely both of them, these two examples. Example 1 and 2, it takes time. Therefore, I can quiz you. This one, it takes time to solve them, and they are super important. I want you to just have enough attention. I push it to Thursday. I solve them for you on Thursday to make sure that you are fresh. Therefore, I have few minutes. I can stop the recording right in here. And in order to help you to not to be loaded with too much of information, I'll quiz you and then I'll solve more problem on Thursday. So thanks for being here, and stay with me to activate your quiz.